I have here a scale model of the first atomic bomb ever used. This bomb, which destroyed Hiroshima, contains about 60 kilograms of uranium-235, of which only about 600 grams underwent fission. Enough, though, to generate an explosion equal to more than 13 kilotons of TNT. The bomb's designers divided the amount needed into two pieces. At the tip, they placed about 40% of the necessary uranium. They loaded the remaining 60% at the other end. A conventional explosion drove the projectile into the target, initiating the nuclear explosion. Now, the exact details of this bomb remain classified because they could still be used. Although this design involves some brilliant innovation by engineers in the 20th century, the really difficult part is preparing the uranium. This lies at the heart of all efforts to stop the spread of nuclear weapons. The key problem? Separating two nearly identical variants of the element uranium. Natural uranium occurs as a metal ore, and it contains primarily two isotopes. Most uranium is U-238. U-235, however, can easily sustain a chain reaction that releases tremendous energy, whereas the more common U-238 will not. Most elements are stable, so that when bombarded with neutrons, they simply absorb them and decay later, or they require very high-energy neutrons, but bombarding U-235 with low-energy neutrons causes its nucleus to split. The emission of these extra neutrons allows the initial fission to generate a chain reaction. So, how do we go about enriching the U-235 in natural uranium? When we separate two items, we make use of their differences. The two major uranium isotopes have identical magnetic and chemical properties. No magnet will tug on one more than the other, no solvent will wash away only one isotope, and neither will boil before the other. So, to separate them, engineers exploit the one small difference between them. U-235 weighs slightly less than U-238. Less than a 2% difference, just enough to make separation possible, but not easy. That tiny weight difference means that the two isotopes will move at slightly different speeds when exposed to an equal force. To enrich uranium for the first atomic bomb, engineers built immense gaseous diffusion plants that capitalized on the differing speeds. A gas containing uranium flows through miles of piping in a kind of race where the lighter U-235 wins out. The gas flows through a tube encased in a chamber. A pressure difference between the chamber and the tube causes more of the U-235 to pass through perforations in the tube's wall. To increase the separation, the slightly enriched stream in the chamber is passed through many more stages like this. To enrich 3% U-235 to 90% takes nearly 4,000 stages. Enriching the uranium for the first atomic bomb required a diffusion plant that covered over 40 acres. It housed a maze of 100 miles of piping. These diffusion plants use great amounts of energy to run. Compressors generating the pressures needed, and the energy to heat gas flowing through the miles of tubing. Another method of separation exploits the small mass difference by using a centrifuge. A typical device consists of a stationary outer cylinder and an inner rotor that spins. A gaseous mixture of the two isotopes flows up a tube along the central axis, filling the rotor. As it spins rapidly, more of the U-238 is thrown out to the edge than the lighter U-235, which stays closer to the middle. The enriched stream can be removed from the rotor and sent to another centrifuge to be separated even more. The amount of separation is exaggerated here. In an actual centrifuge, the amount of enrichment is a fraction of a percent, so a typical plant might have 60,000 centrifuges to enrich natural uranium to 30% U-235. Such a plant uses 4% the energy of a gaseous diffusion plant. Even though this is a much more efficient process, the precision that the rotors need to be manufactured with makes them very difficult to engineer. The smallest defect, and the rotor spins itself to pieces. That's lucky for us, otherwise we might have nuclear devices right next to our microwave ovens. I'm Bill Hammack, the Engineer Guy. This video is based on a chapter in the book, 8 Amazing Engineering Stories. The chapter features more information about this subject. Learn more about the book at the address below.